Hi guys, hope everybody is doing great. My name is Ernest. So welcome to our discussion. So today we are going to look at a branch in chemistry, that is stereochemistry. And this topic basically deals with the concept of trying to study the spatial arrangement of atoms in molecules. And this is going to be relevant for us, especially when we're going to deal with the concept of organic synthesis. Now, this branch of chemistry, which is stereochemistry, is going to find some wide applications, especially in the synthesis of drugs or the drug actions, and also in some areas of organic synthesis that we are going to see, especially in the pharmaceutical industry that I've mentioned, and of course in manufacture of chemicals like dyes. So for today, we're going to look at some of the basic techniques or the skills that we may need to understand some of the concepts in stereochemistry, and how we can be able to regard or maybe refer different parts of atoms which are basically going to be involved in these spatial arrangements. So without further ado, thank you and welcome. So as I've said, today we're going to look at an introductory part of this concept of chemistry, which is stereochemistry. And as I've said, this is a very relevant topic for us to discuss, because in our day-to-day lives, we're going to find different applications of this specific topic. And therefore, we're going to look at some of the fundamental areas which are going to assist us understand or appreciate, in a sense, the application of this specific branch that I've talked about. So by definition, the concept of stereochemistry basically entails the study of spatial arrangement of atoms in molecules. And we're going to see that, and in this we're going to see that the study of spatial arrangement of molecules is going to assist us, of course, develop some of the skills on how we are going to manipulate these different molecules to come up with compounds, or rather some of other molecules that we may of course desire from this specific spatial arrangement of the already existing ones. So therefore we're going to see that this, as I've said, finds wide applications, especially in the pharmaceutical industries and in manufacture of chemicals. And if we try to mention the concept of biological molecules or biomolecules, we're going to see that in order for us to understand the mode of action of these biomolecules like enzymes, etc., we see that the concept of understanding the receptor or the services of these specific molecules in relation to the this concept of stereochemistry is going to assist us understand how they work. So therefore, that gives us an essence of trying to know why this particular topic is relevant. Now, in order for us to go ahead with our discussion, I'm going to mention a few of the concepts that we have learned in our earlier videos, particularly concerning the conformation or perhaps the arrangement of different atoms. I've mentioned this particular concept under the topic of enantiomers and chirality, when we were trying to talk about the concept of chiral compounds, especially in the configuration of organic molecules under the Kern-Ingold Prelog system, and some of the conformational methods that we were trying to discuss. So therefore, just to mention, have a shallow mention of what we had said, which is going to be relevant for us today. I said that the concept of chiral, or a molecule being chiral, this refers to, of course, or particularly this is a geometrical property. This is a geometrical property. And in speaking of a geometrical property, of course, this refers to the orientation of a molecule or an ion, whereby this specific ion that is being referred to as chiral cannot be superimposed on its mirror image. So therefore, a molecule that is being referred to as chiral refers to something that, or rather a molecule that cannot be superimposed on its mirror image. So therefore, we give different examples. And of course, I said that the concept of chirality, or the word chiral, is a Greek word that basically refers to the concept of a hand. And in some literature, we're going to see this one being mentioned roughly, maybe to give it just a historical orientation. And then we're going to see that from this one, if we try to have maybe an illustration of our hand from this, in this particular sense, then therefore we're going to see that if I give this one just an illustration, it's a thumb. This one gives a sense that hand, basically a pair of hands is an image of the object. Let's assume that this is an object and then this is an image. Of course, this one cannot be superimposed. The object cannot be superimposed on its image. Therefore, trying to derive this from a Greek concept of the term or the word chiral. Now we give different types of illustrations that was trying to give us the concept of this non-superimposability of atoms. And then we said that we had different ways we can be able to illustrate this one using molecule. And in this case, I'm going to use the tetrahedral, the star-shaped tetrahedral molecule of a CH form. And this case, of course, applies to the sp3 hybridized types of atoms like the one that I've given. So therefore, I'm just going to give a general representation for this so that we can be able to understand the concept of chirality or enantiomers that I'm talking about. So suppose we have a compound which is CH4. This one we can give a Lewis structure as CH, H, 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 like that. But whenever we are talking about the shapes of molecules, the shape of molecules are based on what we call, or rather they can be predicted by what we call the valence shell electron pair repartition theory, which I'm going to just to write in initials. It's a valence shell electron pair repartition theory. And of course, this theory is based on the principle that the valence electrons, of course, a pair of electrons will be as far as possible from each other whenever we are trying to represent the shape of a molecule. So in this case, if we try to look at this, if I give just a representation like this, from our rough illustration, we can be able to see that this is, of course, a space of around 90 degrees from one another. So therefore, if we are able to just give an orientation that is going to give the widest distance or the farthest distance from each other, then therefore we are going to consider the star-shaped tetrahedral. This is tetrahedral structure in order to give this structure of this compound. This is a methane, of course. So therefore, I'm going to give a different illustration for this, and therefore we're going to see that for us to increase this specific angle, we can have this one carbon located at this particular center, and therefore spread out these covalently bonded hydrogens at these specific points like this, so that the angle between the two hydrogens from this central carbon is going to be 109.5 degrees. So therefore, for our star-shaped tetrahedral structure, it's going to appear like that. And in this, we are, of course, mentioned earlier in some of our videos that we can have different molecular shaped. Now, for our shape, as I've said, is a star-shaped tetrahedral. Therefore, we're going to see that we can be able to represent these line drawings, since the orientations of this particular covalently bonded hydrogens are at different locations or spatial arrangement, so far as the spatial arrangement is concerned. So therefore, I'm going to use the molecular shape that is represented using this particular shape. So I'm going to have this carbon at this specific point. And in drawing molecular shapes, of course, this is going to be based on a three-dimensional space, and it's going to be represented using three specific ways. So the first one, we're going to have ordinary lines, which are going to, of course, show the position of hydrogens which are of course lie in the plane of the board. And the next we're going to have solid wedges, which of course are going to be illustrated using this specific wedge. And this wedge implies that of course this hydrogen is pointing away from or it is sticking out towards the viewer. Of course it's sticking out towards us, and then we're going to have another hydrogen being illustrated by the dashes at this specific point, and therefore implying that it's pointing away from us. So therefore this is pointing towards us, pointing away from us, and this is along the plane of the board. So therefore this is a molecular shape of a tetrahedral structure of this specific molecule. And of course we're going to see that as we said, that this is based upon the principle that the valence electrons will be as far as possible from each other, and now which is contrasting the 90 degrees had given by giving this specific angle at this particular point. So therefore in our stereochemistry we're going to consider this bond angle that I've illustrated at this specific point, and therefore that one having been said and done, I hope that we have understood why we're going to illustrate these specific molecules using such a kind of a shape. So therefore, in giving an analogous example to this, we're going to see that whenever different compounds are formed, there are different atoms that can be able to substitute hydrogen at this specific point. And of course, we're going to see that whenever we're going to have similar atoms like this, in the same case, we can be able to have different atoms substituting hydrogen at this specific point, and therefore forming different compounds. So therefore, suppose I have a general representation for a single substitution of hydrogen, whereby I'm going to have CH3 with another atom X. This is atom X. So therefore, I'm going to represent this specific compound using this X, these specific points for that substitution. So therefore, if we try to look at the molecule, or try to have a mirror image of this specific molecule, therefore, I'm going to have this hydrogen at this specific point, this wedge part at this specific point, the one pointing away at this specific point, and therefore my X is going to be at that specific point. If we try to look at the spatial arrangement of this one, let's assume that this is the molecule, and this is the mirror image of that specific molecule. So therefore, we're going to see that if we try to compare these different types of, different two illustrations for the mirror image and the molecule, we're going to see that this mirror image can be able to be superimposed, or rather this image can be superimposed on its, this molecule can be superimposed on its image. And then the second thing that we're going to conclude about this now is that basically this is going to form what we call two different orientations, or rather two different illustrations, but which of course are going to be shown that the two are one and basically the same compound. So therefore we can be able to see that the object, or rather the image, the molecule can be able to be superimposed on its image. Therefore it's the same compound. Now suppose we had a second illustration of this particular molecule. Now I can be able to do away with this, whereby we have two levels of substitution for hydrogen. This is number B, and this is going to be two hydrogens, whereby we have XY, and our Y is going to be at this particular point. So similarly, we're going to see that if we try to compare the molecule and the mirror image, we're going to see that the molecule can be able to be superimposed on its mirror image, and therefore we're going to conclude that the two are one and the same compound. Now suppose we continue with our substitution, and then we have XYZ. We're going to see that this is going to be or Z. And if we try to look at those two specific illustrations, therefore we're going to see that this mirror image cannot be superimposed. Of course, this molecule cannot be superimposed on its mirror image. Therefore, they're going to form two different compounds. And of course, we're going to see that these two different compounds are going to be referred to as a specific name. And we can be able now to conclude that these two compounds are different and therefore referred to as enantiomers. Now, in not talking about the concept of enantiomers, this basically by definition refers to compounds which cannot be able to be superimposed on their mirror image. So therefore, enantiomers will result for whenever we have a tetrahedral carbon that is bonded to 4 different substituents, such as the case that I've illustrated on the board. Now, suppose I just to give a general illustration for that, I'd say that we had considered the case of a methane, and in any case, if we had 4 different substitutions for X, W, X, Y, and Z for these different atoms, and therefore we can give a general representation for this to represent a molecule that cannot be superimposed on its mirror image. Therefore, it's going to be referred to as an enantiomer. If we try to give an example of such a kind of a molecule, now we can consider a case of a molecule that has substituents like this one. So I can have this one, and then I have a carboxylic acid group, a hydroxyl group at this specific point, and a methyl group at that specific point. So if we try to give just a specific example like this, we can be able to generally illustrate this one as W, X, Y, and Z for these different substituents. So therefore, we have a specific name that we use to refer to this central carbon that is bonded to, covalently bonded to these 4 different substituents, and we refer to this carbon as a chiral center, or a stereogenic center, or basically we can just refer to it as a stereo center. Therefore, whenever we come across these 3 specific terms under our concept of stereochemistry, I hope we're going to understand that they basically refer to this concept of a stereo center. Now, as you can see, I've marked this specific stereo center using asterisk, so therefore we're going to have other illustrations being given as such. Now, as I've said, we are going to find out that we are going to discuss different topics which are going to be concerning the shapes of different molecules. And from this concept of stereochemistry, especially on the concept of chirality and enantiomers that I've discussed, we're going to see that this is a characteristic behavior that is going to be displayed by all amino acids, and other compounds, particularly which we're going to come across as we go by. So therefore, this is going to open for us a window in discussing other topics, of course, which are related to stereochemistry, like the optical activity, and then we're going to look at some of the topics that we're going to discuss about the plane of symmetry, that we're going to see how different molecules, like perhaps the linear molecules, perhaps this one I can just give an example, the radical here. We're going to see that some of the molecules, like the one that I've shown above, can be able to be described using a plane of symmetry. And we're going to see how this one is going to affect the general, or rather the relative spatial arrangements of atoms that are forming different molecules. Now, the essence for us is to understand the concept of enantiomers and chirality. And as we have said, this is the geometrical property of molecules or ions And in actual sense, we're going to see that basically which cannot be superimposed on their mirror images through a combination of different, of course, orientations, or what we refer to as. Just wind up on that. And then next, we're going to look at that we have already discussed in this specific introduction. So therefore, I'll have to wind up it at that particular point. And next, we're going to look at some of the shapes of different molecules that I've talked about and how we can be able to represent them using the valence shell electron pair reparition prediction, a theory, of course, which predicts the shapes of these different molecules. And therefore, that is going to give us a clue on how we can be able to navigate other topics like the optical activities and some of the concepts like the rotational, specific rotations that we need to know under the concept of stereochemistry. So that is it for now, guys. Bye. Let's catch up in our next video. Thank you. God bless you.